All right, welcome to the October 2024 General Meeting of the Minnesota Astronomical Society. We have the moon reflection from Bill Kochen that he took with, I'm not exactly sure what, but I don't know if he's online either to tell us about it. Yeah, a camera. Starting in already, aren't we, Ron? True. All right, so let's go with the little thing. Come on. Oh, my stuff. I know, right? I need my clicker. So now we have the MAS board. You've seen us all and know all of us. And my clicker's not working. Dang it. And we have little stars, and there are important things about the stars. So yes, all the stars are very pretty. So we have everybody here. Everybody's pretty picture. And so what we have, oh, I had that. So because of our board, we are going to be having the 2024 elections. So October, November, December, all very important months for all of us, all of our membership to show up. So we will be selecting for the president, the secretary, and the board member at large one, which is Ahmed's role at the moment. And Jesse, do you want to talk or do you not? Everything here. That slide and the next slide while I get my clicker to work.
Okay, what am I talking about? Oh,
Come on, you can read all of here. Yeah,
oh, it made it bigger.
I did.
For to be nominated,
There you go.
you have to be a member in good standing. And the voter qualifications to elect one of our board members. You also need to be a member in good standing, and members shall not be responsible for any financial obligation to this. Okay, you need to pay your dues. Okay. Yeah. And you can vote in person or electronically. And you may not vote by proxy. And each membership is entitled to one vote. Oh, great. There's a question.
Yeah, I just wondered whether it's in good standing that they can 18 or older.
Yeah. Right. Yeah, a family membership would be one vote and they have to be 18 or over. Yeah. Okay, stop screaming. Calm down. Okay, and to have the election, it has to reach a quorum, which is 10% of the club membership. And what is our membership now?
730.
So that's a lot.
73.
73.
Yep.
Fine.
We need 73 people to show up.
Or online.
Or online.
Yeah.
Okay.
Am I done?
Nope.
Oh.
You want me to take over?
Oh.
It's okay, you can do it.
No, I can't because I need to read.
Okay.
You can finish.
Okay, I will finish. Jessie did a great job. She's a little nervous in front of people, so give her a hand. Everybody, thank you. Perfect. You can go sit down now.
Thank you.
To qualify as being a voter, obviously you have to be a good member in standing. So adult, one family, one person, one payment, one vote. And same thing as being a qualified to be elected. So nominee, thank you. Oh God, yes, I need help. Thank you. And as we said, the election rules, you need the quorum for 10%. Only members attending that night will count toward the quorum. So please, and we will also be doing some elections or registration ahead of time. And we're going to, yeah, I know. And so just making sure that everybody is aware of all of that. So there we go. So how this is going to work. we are going to ask you to be submitting your nominations by email to board member 2@mnastro.org, which is Jessie. And she's going to be doing all of the tallying and nominations. So, but you can nominate anyone. However, that person that is nominated also has to accept the nomination to go onto the ballot. So you can nominate everybody, but just make sure that they're okay with it. We're going to be holding the deadline, which is the day before our next meeting. So Wednesday, November 6th, 2024 at 9 o'clock, that email has to be to Jessie or board member 2@mnastro.org to count. So that way we have time to make sure we have the next plan in place for the general meeting. Otherwise, we're rushing for everything. So just keep that in mind. And that will also be our 60-day notice at that point for the November meeting to saying that we're going to be voting in the next 30 days. Well, we have to note it between 60 days and 5 days for a meeting to happen. There's a little tidbit in there. And so then on Thursday, December 5th, online and in person with the registration from online Zoom, we're going to be sending that out. Here in the room, we're going to be doing ballots and making sure that you have one per family member, that you are have paid your dues, you're valid, everything like that. So, and it'll be roughly about 7 o'clock when we start the meeting, but we'll be having some discussion. So it won't be exactly at 7 o'clock, but be here by then. All right. And if anybody has any questions, feel free to give us a shout. Looks like you have a question. Okay. All right. Does anybody else have any questions? Any especially new members that haven't been through this before? Okay.
Thank you.
And then we get to welcoming new members. So welcoming our guests that are here and all of our new members that are online and in person. And yay! And I think I forgot to do a new slide. So forgive the next slide, but thank you everybody that has joined. And I tried to be funny for Halloween and it kind of backfired because I forgot about it. So the cat and the witch are covering up the moon for Halloween. So, because moon is, yeah, it's funny. But anyway, it was supposed to be there. But anyway, so we are having some interesting events this October, besides the cat being on the moon. We have a Ornid meteor shower and the Taurid meteor shower, which hopefully will be massive this time. But I also know the next few days we have some solar flares that have been happening. And so we should get some auroras this weekend. So that'll be nice. And yeah. Oh, and yesterday's annular eclipse, but yeah, not here, but I did do that on the last month. So, because all of this goes from meeting to meeting, not month to month. So it's all between our meetings. Ahmed, do you want to talk about the Loaner Scope program? Okay. Antone is not here. So Loaner Scope program is something that we do for our club membership. You are allowed to sign up via online and have a telescope that you can borrow for a month free of charge, just for the price of a membership. Doesn't matter if it's the regular or the patron or even the student if you're a student. And so that includes, I think, almost 18 or 19 different telescopes that we have. And it's very easy to go through to our main website, click on membership, go to Loaner Scope program, fill out the form, and then Antone will get in touch with you and arrange a meeting and show you how to use it. We also have the great courses CDs, which are workbooks and audiobooks that are along with that Loaner Scope program. So if you wanted to borrow that for a little bit, you could certainly do that. And like I said, it's 30 days. And on some of these, you can actually extend it out to 60 days unless somebody is requesting it. And then, but that will be in touch between Antone doing all of that. And then, yes?
There was a question about online about one of the something.
Okay.
and it's short.
That's it.
So the question is whether you need a magnet ELO.
Well, that brings me to Doug Neverman and his ELO site report, which he will be happy to answer for that. You want
Am I on?
You are on. Do you want the
My
clicker?
name is Doug Neverman. I'm old, I forget. And hopefully nobody exchanges cards on me, so I know what's going on. I'll address your question a little bit later. I need the clicker. Oh, it's not your question? Okay. Now, I know. It's Steve Emmert that's asking? Okay, that tells me how to answer. All right, so I am the chair of the ELO committee, and every year, then everybody, all of the chairs of each of the site needs to get up and give a little presentation. So this is mine, whether you like it or not. Our mission, if you read the bylaws, we really have two things that we do within MAS, and one of them is for us to gather together and do astronomy together and talk about stuff that nobody else cares about. But the other part is then doing public, working with the public, and there's a lot of activities that we do. ELO facility, Eagle Lake, is one of the places where we do a lot of star parties, but we're going to get into some numbers a little bit later. And you'll see that we're actually, there's a lot of people that come out during or impromptu star parties. And we'll look at those numbers. If you don't know where we are, located west of the metro, drive down 212 to get to Norwood Young America, and then at the last stoplight, turn right. I got to think about that. I'm dyslexic, so turn right. And we got three buildings that you can see here. The Onan Observatory, the classroom in the background between them, and then CASB on the left-hand side. We have lots of equipment out there. We got two slides on the platforms. I'm not going to spend a whole lot of time on them. But just to let you know, I've made sure that I think I got all the right stuff now there. But we have quite a bit of equipment that is very, very nice. We have a 20-inch obsession out there. On the imaging, we do have now the Maxitov. Now, the story on the Maxitov is that in Doug Surge is not here. He's the one that's in charge of the imaging platform. But as last year, we realized that two of our telescopes basically had the same field of view. So we decided to put in for, and it was approved to put the Maxitov. Sorry for the misspelling. I saw that this morning. It says, well, Trina already has my slides, so. So it actually is there to provide a little bit different field of view. It's also good for viewing planets. So we have the Malincam camera, which doesn't really take pictures except to send them out on a video, and we can look at them that way. So it's a long. I guess I didn't put down the focal length on it, but it's quite long. We also have binoculars out there and some personal solar telescopes that can be set up. So there's a lot of equipment out there that can come out and be used. The ELO committee, there's 7 people. There they are. This year we set up teams, and there is a representative on the from the committee on each of these teams. So we've basically kind of tried to farm that work out so that there is a particular team that is interested in a particular area, and address those and then bring those to the committee. I do have some numbers here. So we had, you can see our attendance at our spring, we had 19 scheduled public star parties. And only three private star parties, that's actually down from last year. or from years past. And then the impromptu star parties. Now, so the public star parties, you know, are for public, but then there are lots of people that come out and use the ELO facility. Some of them just to set up their equipment, and then some of them to actually open up the building and use the telescopes that are out there. So I looked into forums, and we had about 60 star parties where people said, impromptu star parties where people were just going to show up and set up their equipment. Now, 18 of those had closing sheets. So there are sometimes people come out, use the equipment, and then close it up. But most of the time, in terms of the impromptu star parties, people are just coming out, setting up their telescopes, doing whatever they want to do. Most of them are taking pictures, like me, and then closing up and or going home. And the buildings don't really need to be opened for that. So it's available for more than just public star parties. So if you got a telescope, looking for a place, you're on the west side, come out to ELO and set up. We ask you to put something in the forums that say you're coming out. This is something we started during COVID, just so that we could track that, but it's kind of continued on, that everybody signs up, tells us that we're, tells everybody that they're coming out. I also have a chart of basically the attendance for public star parties and total attendance. So yeah, something happened in 2020, and it went down. But these are all based on the numbers that are on the closing sheets. They're an estimate of how many people came to that who have come out, and oops, wrong way. I pushed the button. Yeah, 2019 down, and I don't know why. Yeah, somebody was mentioning that 2019 looks like it's down. The one thing I will say is that the 2024 number was as of 9/22. This past weekend, we had another star party, and there were hundreds of people out there. I see some people shaking heads. There were lines. I think I heard Dean was down in Casby, and he had a line that went out the door, and it never ended. And it was busy for about an hour and a half, 2 hours. Bernie was there. He said 2 hours. Clayton, did you have a question? The question was, why are we getting bigger numbers? And to tell you the truth, I don't know why. Now, I do know that on this past party, there was a busload of University of Minnesota students that came out. So, and I don't know how many, whether it was one buses or two bus or whatever. But so that pushed the number up a little bit, but probably not by hundreds of people. So, yeah, I don't know why. If you kind of look at it and, you know, try to ignore 2020 and 2021, it looks like there's a trend up, but I didn't do any mathematical fit to linear fit to see whether the line goes up, and certainly 2020 and 2021 would throw that data off. So we're getting a lot of people coming out. They're actually lots of fun to come out to the star parties and talk to people that are there and visiting. We have key holders that help run the telescopes and crowd control, but it's just fun to come out and talk to people and see them and see how excited they get when they get to see Jupiter in the telescope.
Would you welcome people out just to go out in the plaza and
Sure.
set up their own?
Yeah, come out. In fact, I've taken my telescope out there and set up, and people come and use it. I have a star sense, so you can use it as a push to. my job is a push to with using my cell phone. And I say, well, here, push it to get the picture in view. So let them actually use it while I watch them very carefully. Excuse me, Jenny? The plaza was very, very crowded. Yeah. Yeah, it was beautiful weather on Saturday night, so the parking lot was full of cars. Yeah. Clayton, I wish I knew what was going on with the numbers and why people are coming, and maybe it's just word of mouth that's getting out there. It's a good thing, right? Yeah, yeah. Well, I'm not sure whether this includes the Aurora, but this might be just the public star parties are there, man. Yeah. So yeah, a lot of people come out and see, oh, there's this here. Well, what's that all about? And find out and then come up. So yeah, one comment was that the membership is higher and then they invite friends and family out. All right, I think I have one more slide. This is work that we've completed. The sidewalk lift is done. We no longer have to worry about people tripping in the dark on the sidewalk. We've had a structural evaluation of Onan that's been going on. We actually have a team that's in charge of doing that work and recommending what comes next. Something I have to talk with them. We have had problems with a bifold door in that the motor that closes that door has broken in the past, has not worked. And then it gets very, very tricky because as soon as you disengage that motor, that bifold door, about 900 pounds, is going to come down and hit. So we put in a backup, a bifold door backup that we need to, there's 3 people trained how to use it. It's one of those things that probably normal key holders will not get trained on because there is a lot of danger in doing this particular work. So and we put on densifier on the CMUs to try to help prevent water from getting in. We still have work to be done. The Onan structure work will continue. We have a recommendation from a company that did an evaluation a couple of weeks ago that I haven't shared with the board yet, I don't think. But and out of that, we're going to be figuring out what needs to be done next on the Onan building to help keep that working. There's also a focus motor that we want to put onto the one of the imaging rigs, I think on the C-14, which is good because I remember when I first started taking pictures, I would get myself in focus. I would look at my pictures and say, I really got focus good this time. And then I would go home and look at my pictures and they would be little donuts, which means I was out of focus. So a focus motor is good. We have Bahtinov masks that we use, but this will be a little bit easier. Changes over this past year, besides the work we've been doing, we've changed training a little bit to make it a little bit easier. We're done with that. We do have some problems that we'll address in the committee and figure out how to do training difference. And changes then we talked about the telescope that was added. That's it.
All right, perfect. Thank you, Doug. Okay. Are we going to be doing any special events for the comet?
No.
No, not at this time. And-
Friday is on the 12th.
No,
I lost the mic.
That's a mic.
I lost the mic.
Sorry.
Astronomy Day is on the 12th, as I showed in one of my pictures, so.
Yeah.
Yeah, and there's supposed to be aurora apparently in the next couple nights, but we're not opening for that either. We did that once and it ended up to be very, very difficult to manage all of the people with very few people, key holders in place, because we just kind of opened it at the last minute. And we decided in the committee, no, we're not going to do that anymore. So, that's true.
You don't need an observatory to see the aurora. You just need to go outside away from the city.
Yeah.
Exactly. I mean, they know it's a popular place and they can find it and you go from there, but just, you know, driving out there and not even getting there, you can still see it. But thank you, Doug. And I think I saw Jerry here. Is Jerry here? Okay, he says no new information, but we're going to wait until next month. Oh, and hold on, let me get to the right one. Okay. Hey, get out there and observe. Okay, come on. That's Jerry's line. Yes, get out there, observe, and take images. Or what it? Or image. Okay. Sorry, I'll have to update the slide. Maybe one of these days I'll get it right. So speaking of upcoming star parties, ELO, October 12th for Fall Astronomy Day. And then September 26th, 7 p.m. Come out there. I'll be talking at that one. And then the BSIG is still at Metcalf at October 19th. Earlier time.
That would be October, is that September 26th next year?
Yes. All right. So October, apparently the find and replace did not work. But that's all right. We all know that it's October now. We're not going back in time. And yeah, no. So thank you. Thank you for catching that. I appreciate that, Doug. Yeah, I'm challenging everybody to find my mistakes. You know, you all are doing a great job. Huh? I think so. I'll try and bring prizes next time. Yes. Okay. Yes. Yes, I will get to that in just 1 second. Yep, I will. Yep. So are you a member or a guest? Oh, excellent. Perfect. The Cherry Grove is having some happenings this weekend. We have the mini Messier Marathon, or the 4M, and we'll be starting that roughly dark, of course, and having, mini challenges along the way. So please come out to Cherry Grove. This is a little bit more of a relaxed thing, but we'll get there. And key holder trainings. What?
I'm sorry, you don't know about this, but the ELO, the October 5th is postponed.
Oh, the October 5th is postponed? Oh, for the training?
For the ELO.
Oh, okay. Well, there we go. So now everybody can come out to Cherry Grove. Yeah, because ELO is postponed on October 5th. And apparently I didn't make myself a slide. But anyway, key holder training for October 5th starts at 6:30 at the observatory. We're going to do the warming house first. And then as we go throughout the night, we'll do the LX200 and the BAD. Just send us an email or post on the forum that you're coming out. The BAD is the big aperture Dobsonian. It's a 24-inch Starmaster, which we have nicknamed the BAD. And yes, I did have to think about that acronym. If anybody knows why, they can ask me later, or doesn't. Exactly. So there. I don't have any other public service announcements. Does anybody else have any? Okay, perfect. Moving on. Gemini articles. I believe the last one has been posted. Is that correct, Mr. Faulkner? Okay, Gemini for October has been published. And so the next one is to get your articles in between auroras and equipment and your successes and imaging tips, your challenges with your imaging for the Astronomical League. You can write an article for that, Mr. Doug. You could. It would be interesting and lovely for other people to read. Yes, yes, it would. So that is due November 10th to be published in December. And we will also be publishing the election nominations as well. And the results, of course, in that at that time too. If there's any other happenings that you have going on, please feel free to email the secretary to put it into the happenings that week. And those are always nice to read too, like the CGO training. Due on Thursday. Thursday of the following Tuesday that it goes out. Previous, yes. Yes. So it has to be due tonight if you want it published by next Tuesday. Okay, there we go. I'm going back in time. Yeah, my September date, yes. Nope. I don't know. Has anybody been counting? How many mistakes have I made in the last year? Year. Okay, everybody lost count. Great. 147? 1,247. Okay, well, thank you, Claire. Sorry, excuse me. The November meeting is going to be a little bit of a challenge for us. We're going to be doing it online only. The room here is being booked for a kindergarten school event. So we do not have it. Otherwise, we would really have to delay our meeting to September 21st. And that's just too long. We want to have our elections on time with notifications and introducing all of our nominees. So next meeting, November 7th, online. Don't come here unless you want to just sit in the waiting room and watch it on your phone or your laptop. So you can sit at this. Why not? Yes. Well, you know, the kindergarten event might be more impressive than this. True. And yes. Yep. So you go to the main website and it's on the calendar. You just look for that general meeting time and click on it. And then scroll down and about middle of the page, it'll say, click this link. You click the word link.
Also be in the happening.
And it will also be in the happenings. Compliments of our secretary, Mr. Dave Faulkner. And yes. Oh, okay. Well, and then Ahmed's telling me that it'll be easier because we'll be on the homepage. But in any other time, click on the calendar and we'll do all the other stuff. So it gives you website access. And then we'll have Professor Michael Coughlin? Okay. Anyway, he's going to talk about gravitational waves. But for tonight, and I think we're actually doing pretty good on time, we have Professor Terry Jones. It's your turn to be up here. Yay! And it'll take me just a minute to switch things over. So hold your questions or any comments at the moment. Feel free to email me that I have been weird tonight. And he does a DART mission, polar astronomy.
All right. Hello, everybody. My name is Terry Jones. I'm a professor emeritus at the Minnesota Institute for Astrophysics. This is my 5th or 6th time, I think, coming to a mass meeting. Used to be, I remember when you were back in the museum, and I don't even know, I might be even before that. It's hard to say. I was saddened to hear that Lauren Nelson had passed away. I didn't know that. But he was usually the one who contacted me all the time. All right, so I do infrared polarimetry is my main thing as a profession, but that's a kind of a dry sounding sort of a subject, right? Although I hope to pep you up a little bit about polarimetry later. But there's a very interesting paper that came out early this year on the results of the DART mission. And so I'm going to talk a bit about smacking things into each other. And we'll start with why the DART mission was originally proposed and took place, and that is planetary defense. Now, if you type planetary defense into Google, this is the most common picture you will get. This is not what we're talking about, all right? This thing is about half the size of the moon, and if it smacked into the Earth at orbital speeds, it would probably liquefy the upper mantle. So not even cockroaches in grandmother's, soup from the Christmas last year would survive this kind of a thing. What we're interested in are preventing or dealing with objects more like this. And the object that you just saw in that picture, the Earth, since the formation of the moon, has never been hit by something that big. So it's not going to in any time we need to worry about. However, the Earth has been hit by things this size, all right? We're talking every 2,000 years or so, getting something at around a few hundred meters in size, which can, when it hits the Earth, can explode with about with about 1,000 megatons. That's about 2,000 conventional atomic weapons. And so that isn't going to, a few thousand years, something around 250 meters. That's smaller than these, all right? No, it's a very steep function of size, right? I mean, after all, the Chicxulub impact, which was once every 100 million years, was 10 kilometers across, and here, right? So it's very, very strongly. But then the smaller the asteroids get, the more there are, and it's a very steep function of size. So we get hit by little things all the time, and medium things like Tunguska, that event, that's every 100 or 200 years, all right? So the question is, if we have something that's going to be on this size scale, which would not wipe out civilization or anything like that, but it could hugely impact life on the Earth for quite a while, can we do something to prevent them from hitting the Earth? And of course, your immediate thought might be, let's go blow it up. And that's a very bad idea, because that guarantees some parts of it are going to hit the Earth, right? Because there's no way what you want to do is you want to nudge it out of the way, all right? So NASA has developed I think some movie producer got a hold of NASA and said, you need a good looking representation of what you're doing here. So NASA's into this, of course, and if you look in the upper right, there's search, detect, and track. So that means you're using telescopes, both space-based and ground-based telescopes, not very big ones, by the way, who scan the skies looking for asteroids, and then you try and plot their orbit and see if they're going to smack into the Earth. Up in the upper, in the upper left is where you assess how dangerous they're going to be, what orbit they're going to be on. Now, NASA used to talk, put out little bulletins now and then that it found something that might, with a 1 in a million chance, hit the Earth. And they stopped doing that because they kept getting a big news story every time. Killer asteroid on the way, right? And this was when U2 and things like that were starting to get going. So that there was a lot of money to be made by having your clickbait image there with an asteroid like the one I just showed you at the beginning smashing into the Earth. And there's something the size of this building that might in 1 in 1,000 chance hit the Earth. So NASA doesn't do that anymore, but they do assess whether or not there's a likely impactor. Now, you also in the lower right hand corner want to characterize the object to see what kind of asteroid is it. Is it a rubble pile? Is it a big rock? Is it got carbon-based material on it? Is it a rough surface or a smooth surface, and things like this? And that's what I'm going to be talking about a bit here tonight, all right? And then your plan and coordinate, I don't have a clue what that means, but the DART mission is over here on the lower left, and that's for mitigate. How are you going to deal with a potential impactor that's on an orbit that could smack into the Earth, all right? So the paper I want to talk about has that word in it, polarimetry, which most astronomers, I don't know, I'm going to try and convince you amateur astronomers there's something to be done in polarimetry. But most in my profession run out the door so I always avoid saying polarimetry when I talk about things. Anyway, it's a binary asteroid, and I'll explain all this in a moment. And that's an artist impression of the DART mission heading to smack into Dimorphos. All right. And what they did is they did polarimetry of the asteroid before and after. And I'll explain to you what's interesting about that, why that tells us something we wouldn't necessarily know otherwise. So what is DART? What has polarimetry got to do with it? And what did they find? Now, if you want to send something to an asteroid to hit it and move it out of its orbit, all right, that's the basic idea. You get a big lump of aluminum. Aluminum's cheap. And you put some rockets underneath it and you send it out and you smack it into the thing. And you want to know how much does it move, right? Now, you don't want to just hit any old asteroid out there, because if you hit an asteroid in orbit around the sun and you bump it a little bit, you could save the Earth, but it's going to take a long time measuring its orbit, hopefully without any other effects taking place, to figure out if you've done anything. So what they've done is they've chosen a binary asteroid. This is Didymos is the bigger asteroid, and Dimorphos is the smaller one orbiting it. And what they did is they came in and they smacked into Dimorphos head on in its orbit. And now all you have to do is measure the change in the orbital period to know how much momentum you transferred from your chunk of aluminum to that asteroid, right? And that can be measured very quickly and very easily just looking at the light curve. It's just simply photometry and measuring the light curve. And it was quite a significant change. Now, you might wonder, didn't Isaac Newton centuries ago figure out, how you exchange momentum when you collide things together? I mean, we've all played pool or billiards or something like that at one time in there. Well, what is there to know? Well, it turns out it's very uncertain what's going to happen. So if you have a perfectly elastic collision, like a billiard table, and the incoming impactor bounces straight back, you've transferred what you think will be the maximum amount of momentum to the other one. Slowed it down as much as you can. If, however, you have an inelastic collision where the incoming object smacks and sticks, you've transferred what you think is the least amount of momentum to that. And there's only a factor of 2 between those. So what's the big deal? Factor of 2, just put some more aluminum on the thing and you'll be good. The problem is that if you come in with an impactor, it could in fact splinter and take pieces of the asteroid with it off in a cone. And now that momentum's heading off and has not gone into slowing down your asteroid. The other thing that could happen is you could come in and the energy of the impactor could go into blowing out material from the target in the other direction, and you'll even get more momentum transfer than you would have thought you could. And in fact, that's what happened in this case. Luckily for us, the impactor came in, released so much energy into the inside of Dimorphos that it blew a big hole back out the way it came in and slowed it down quite a bit more than they expected. So that was a success. Now this is Dimorphos. It's about the size of US Bank Stadium. If you took the lid off US Bank Stadium, this thing would just about fit in it. Just about right, okay? The impactor is about the size of a refrigerator, solid aluminum. So imagine standing outside US Bank Stadium and throwing a refrigerator-sized chunk of aluminum at 20 kilometers per second. That's the hard part. into Dimorphos, all right? Now, the project, the DART mission, did not have any science instrumentation on the craft itself. It had a camera, and that's what took this picture, and that was strictly to do fine tuning of the direction so that it would hit smack down in the middle. There was a CubeSat, and CubeSats are kind of an interesting new thing. I don't know if anybody here has anything to do with CubeSats, but they're about this big. and you have a standard package with wire, with power and things, and you can put, a roach in there to see if it survives in space or something like that. If you're a high school group that got chosen by NASA to do these things. But anyway, there was a CubeSat on this experiment that was let off before it hit Dimorphos, and it'll take some pictures that you'll see in a moment. But at any rate, the last picture before impact is this. So the medium-sized rocks there you see are about the size of a car. And so you can kind of imagine that a refrigerator is about a quarter or so the size of one of those. So that is the size of the impactor. And when you think about it, it seems kind of small, but it is going very, very fast. It's going at orbital speeds, and that's what gives you the advantage. Okay, so it was a 600 kilogram refrigerator, high size thing. It came in at 6.6 kilometers per second, and that's a kinetic energy equivalent to 6 tons of TNT. All right. Now, if you set off 6 tons of TNT inside US Bank Stadium, it would be toast, right? Right. But remember, US Bank Stadium is mostly air, right? There's a concrete shape around it, but there's Dimorphos. Appears to be a rubble pile, but we're not really sure what's inside. We'll see that what's inside is different than what's outside, and we know that because of the experiment that I'm going to talk about. So the experiment was about 3.5 times sticking. So it was more than you would get if you had a perfectly elastic collision. And everybody was very pleased about that. They had some very wimpy sort of criteria to say it was a success. And it was so much better than that, they felt kind of embarrassed for having said, all we need is this for a success. And they had this huge excess of momentum transfer. Now, that's good. That means we can send refrigerators and smack them into asteroids and prevent them from hitting the Earth. And we'll be able to calculate how much we need to do. So the orbit, which was a 12-hour orbit between these two, changed by 33 minutes. So if you were there doing photometry with your telescope, and you can get a 33-minute change in the light curve, no problem, right? So this was a very a good idea to have done. It made Dimorphos a term we use now called active asteroid. We used to think there's asteroids and there's comets, okay? Well, it turns out that there's everything in between as well, right? And so this asteroid, for example, if you took Ceres, the largest asteroid, and brought it too close to the sun, it's mostly ice. It would sublimate and become a comet, the biggest comet you could possibly imagine, of course, but it would become a comet, right? Now, Dimorphos had no water in it, but it did have a lot of dust and dirt and rocks and things. And so when it was hit and all this stuff splashes out, it developed a tail, like a comet, right? And lots of objects in the solar system are capable of having that happen to them, and they give them the name active asteroid. Now, Dimorphos only lost about 0.1% of its total mass in this process, which is kind of interesting when you consider what it was hit with. Lots and lots of papers came out about observers who looked before and after. Right. And I just show this just to show you that, NASA was, of course, telling people what's happening, and everybody's there with their telescopes looking, trying to see what it's like before and after. And we're interested in the polarimetry. Now, here is a picture from the CubeSat right after impact. And the reason there's those squares there is they're trying to get different brightness levels all on the same image, all right? So if you just had this with one brightness level, you would only see the center blob and you wouldn't see anything else. If you want to bring up the fainter outer regions, you would do that. And you can see Dimorphos is in the upper left, Didymos is down on the lower right, and dust and dirt and little pebbles and rocks and things have been spewed absolutely everywhere by the impact, okay? All right, now that's all the fun stuff. Let's talk a little bit about polarization, okay? Now, I'm sure most of you understand that polarization means the light vibrates in one particular direction. So if you've got sunglasses that are Polaroid sunglasses, if you ever have Polaroid sunglasses and you're standing on a hallway that's lit up from a window at the end and somebody just waxed it and it's nice and smooth, take your sunglasses and rotate them and you will see that the light reflecting off of that floor is polarized. And sunglasses block the polarization that goes this way. So you will have to take your glasses and turn them like so, and you'll see the floor will brighten to do that. Now, why do sunglasses block the polarization that way? That's because reflections polarize in the plane, perpendicular to the plane of scattering or in the plane at which you're looking. And that's what you're trying to block with Polaroid sunglasses. If you have Polaroid sunglasses or a polarizing filter or anything, go outside and look 90 degrees away from the sun and rotate your sunglasses and you'll see the sky has a dramatic change in brightness. The sky is almost 100% polarized 90 degrees from the sun. And many photographers use that in order to enhance photographs and things. So for example, you can have the sun setting over to your right and have a model or an object or somebody you're taking a picture of there, and you can turn your polarizers and make the background black because that's scattering 90 degrees from the sun. So polarization is a normal everyday part of light, and it's also caused when you have scattering, all right? Now, if you look at an asteroid, you're looking at light reflected off the asteroid, and that light can be polarized. But the way it's polarized depends on what kind of surface that asteroid has. So let's get a couple of, that's a long explanation of where we're going here, but let's get a couple of thoughts here. So we're going to be looking, you can see there's the sun on the left, the object we're looking back on the right, and we're down there with that kind of funny looking eyeball down there. And those 3 points make a scattering plane. And so we're looking at the object, and over to the side is the sun, and the sun is illuminating the object. And we're going to reference the polarization with respect to that plane, right? Just like when I looked at that floor. So the scattering plane, when I look at that floor, goes straight through me and over my head. So there's the window, down to the floor, up to me. Those 3 points make a plane. Normally, the light from something like that floor would be perpendicular. The polarization would be perpendicular to the scattered plane. It would be vertical on this diagram. But the polarization could, in principle, be in the plane of scattering, and that's going to be the horizontal line you see there. You don't expect that. If you look at the floor, you will never get that polarization. You don't expect that, right? Now, what? Okay. Oh, there we go. Wow, that's weird. It doesn't like that slide. Well, maybe we have some, let me see if it shows up in here. Okay, that's a shame. All right. So we're going to have to explain to you, boy, I hate talking about what a graph says when there's no graph there to look at, right? That would be a graph that we would use that where you plot, don't even worry about it. It doesn't like the picture. It must be, right. Anyway, what you would see here, if you could, is a graph, and we would have a vertical axis. That's the polarization. Only it's not P, it's how much is this way or how much is this way, right? Vertical and horizontal polarization. Vertical is positive, horizontal is negative. And so it's a way of using the sign, positive and negative, to tell you if I'm looking at light that's polarized this way or light that's polarized this way. And we expect it to be positive, right? We expect it to be perpendicular to the plane. And if you look at the sky, it's always that case. If I look at the sky and I look right at the sun, which you should never do, of course, I get no polarization. And if I look at the sky, it gets more and more and more polarized until at 90 degrees, it's 100% polarized. And it's always perpendicular to the plane of polarization. However, comets and asteroids don't do that. They have, well, you wouldn't expect them to go to 100% polarized. It's a surface after all. Now, that floor, that nicely polished floor is only going to give me 10, 15% polarization, right? But if you look at comets and asteroids, they transition at about 20 degrees. So I'm looking at the sun and I go off 20 degrees and I see that asteroid over there. It will have no polarization. And the polarization at larger phase angles will be what I expect it to be, positive, perpendicular. But at between 0 and 20 degrees, it has negative polarization. Something funny is going on. And I think the best way to explain that, all right, now what's happening? Let's see here. Or did I do that when I clicked over there? I went out of slideshow. I think we just need to go back into slideshow. And I think you would do that up here someplace. No, that's, we're in the sorter at the moment.
Okay, well, we're gonna.
There we go.
Okay, let's.
You are screen sharing. Just say stop share. See what happens. Up.
That's yeah. Hi, Steve.
You might want to try hitting slideshow again there. That's the one.
Hold on. Yep, I gotta share again.
All right.
Trying, people, we're trying.
We're up and going. Let's not try and let's not tempt fate. Okay, so what's happening, right? Why is this mean anything? What's happening here? Well, if you have a surface that's fractal, in other words, it has structure at all wavelength scales, from little tiny to big. So it's, you could imagine if you went and you took sand and smaller than sand and smaller and smaller and smaller and smaller and just mix that all stuff together in a light fluffy surface. It's exactly what the surface of the moon is like, for example, okay? Now, when light comes in and strikes that surface, unlike my nicely polished floor, it doesn't scatter the same. The light goes in and rattles around into all these structures, and it can come out polarized the wrong way at low phase angles. And that's what's happening. What that tells us about asteroids is how dark are they and how rough are they? Okay. All right. Why am I not getting the next slide? We must have really freaked it out with that one slide. Right. So, all right, here's a graph that shows everything anyway. It's just that I needed a, right. So if you look on the left, those are comets. And we're looking at that funny way we do polarization, positive and negative, perpendicular and parallel. And then we're looking at phase angle. And most of the work on there was done by us at the University of Minnesota. That's one of our things that we did. Now, if you had tiny dust particles, specks, or the Earth's molecules in the Earth's atmosphere at 90 degrees, that would go up to 100% polarization. So you can see this is different. Now, if you look at the lower left, you can see the negative branch, we call it, and that's where the polarization gets negative. Most comets behave the same in this. They all look pretty much like Hale-Bopp was different. Hale-Bopp was a peculiar one, and that's the big squares that you see there. But otherwise, most comets all behave the same in this plot, in this diagram. Below are 3 asteroids, and the first thing you're going to notice is that they're different than the comets. Ceres goes down like comets do to around -2% on this, comes screaming up like comets do. Pallas, not so much, but Vesta has a very weak and shallow polarization versus phase, right? That's because the surfaces of these asteroids are very different from one another. Ceres is a very carbonaceous, powdery kind of surface. Even though it's mostly ice inside, the surface isn't. Whereas Vesta is more like bare rock, okay? So now we are armed with a tool to look at our poor little asteroid that got hit by that big chunk of aluminum before and after. Yes. So what you see on the left is the B filter, and on the right is the R filter, just blue and red. You're probably quite familiar with the filter notations. And the black line and dots, that's the polarization curve before the impact. And the one to the right, blue or red, is the polarization curve after the impact. And you'll see it's different. The polarization is lower. So whatever it was that was excavated by that probe smacking into it and blew out the hole was different, right? And the way it was different is that it was brighter, lighter stuff. It was lighter colored stuff. It was a higher albedo. It was whiter, right? Now, what does that have to do with the surface characteristics? So if your light comes into my rough surface and it's going to rattle around before it comes out, it's that rattling around that reduces the polarization. If it was just one scatter, like off my floor, it would be highly polarized, but it's not. And that's because it rattles around inside, the light going between all these little specks in this fluffy surface before it comes out. Now, if I make the material darker, that second and third and fourth scatter get absorbed. So I only get one scatter and I get good polarization. However, if the stuff is very high albedo, it's white. It's like sand, like white sand on a beach, instead of dirt, dark dirt. Then the light rattles around a lot, gets its polarization all messed up, and comes out lower polarized. So when this object smacked into poor, this is up to months, up to a few months, right? Right, and you'll see in a moment that apparently nothing changed in the polarization characteristics for all these months after the impact. Whatever it is that came out coded everything. Poor Didymos is over there just covered in this stuff, right? That it was blown out from its companion. Now where was I on this? Okay, so in comes the impactor. It blows out stuff, quite a bit of stuff, as it turns out, 1/10% or 1 part in 1,000 of the entire asteroid that it hit. And that stuff went and coated everything in the two of them in the system and blew out into interplanetary space between them. And that stuff was higher albedo stuff. It was whiter, lighter, reflected light better than the stuff down inside. Makes no sense. If you looked back at Didymos, at Dimorphos, it looked like a rubble pile. Why should the stuff just under the surface be any different than the stuff on the surface? It was just, the solar system took a big shovel and put it all together in one place. It's not, but apparently not. Apparently what's inside is fundamentally different in its characteristics than what's on the outside. One possibility is that the outside suffered from space weathering for thousands, if not millions of years, but still, it's still a bit of a problem as to why would something this small that looks like a collection of rocks, like in a bucket that you just poured out into space, be different on the inside than the outside. But it is. Okay. So this is some pictures, so to speak. This is kind of hard to explain, but basically what I'm looking at is I'm looking at the system, and you can see the comet-like tail coming off. These are pictures, and they're in polarization, and that's what's on the right-hand side is the polarization. And what you want to notice is that the polarization is pretty much the same everywhere. It's orange everywhere, it's yellow everywhere, it's blue everywhere, where the polarization is of a particular level. And that means that there's nothing evolving in this system after you smacked it. There's nothing is being dissipated into the interplanetary space, leaving the original surfaces behind. Rather, everything got coated and it stayed pretty much the same. Right. And this means that even though the solar wind and the sun's radiation is blowing this stuff out in a tail, it's not taking away one type of dust compared to another because it's the same polarization everywhere. No way we know how to explain that yet, but I'm sure somebody's working on it. Okay. So the conclusions from that study are that there was a dramatic drop in polarization immediately after impact, likely higher albedo. And the drop is long-term, indicating a persistent dust cloud and or deposited material. The ejecta formed an extensive and persistent tail, little variation in polarization. And the polarization that you see most closely resembles what are called S-type asteroids. Those are asteroids with normal magnesium, aluminum, iron silicates, as opposed to carbonaceous asteroids, carbonaceous dust, or something else, right? So this was just a bunch of rocks. If you went outside in Minnesota and dug deep and just took all the rocks and dirt and stuff you could find and got rid of all the water in it, that's the tricky part, you would have stuff that looks like an S-type asteroid. But for some reason, what's just underneath was different, was a higher albedo material. Okay, what I want to talk about just for a moment, any questions on the impactor and that sort of thing first, because I just want to kind of pump up the possibility of amateurs doing a little polarimetry just to excite themselves. Yeah.
Approximate that reaction.
There you go.
What I'm wondering is what sort of research or investigation has been done into the possibility of a naturally occurring or a man-made material that could approximate that polarization?
Right. Well, anything that's a very, very fractal, rough surface. What do I mean by that? I mean, they're not all the same size particles. You have all the little ones and the big ones. That will do that. And you can do that in the lab. They use something called a goniometer. I love that name for the instrument. goniometer, right? Can you imagine, telling your students, all right, now you're going to use the goniometer today, right? And they'll all be probably wondering if there's some kind of exam for their medical status or something in that. And you can put different types of material and surfaces and get this result. If you've ever heard of something called gold black or carbon black, that's a way of making surfaces extremely black to your eye. And it's not because of just the fine powder. The fine powder is stuck into all these fractal forms. That will do the same thing, right?
The impactor itself was made out of aluminum. Did its signature show up, or did it coat things as well? Because it probably went molten.
Good question. And the answer is no. Right. First of all, the amount of aluminum is trivial compared to even the ejecta, right? Remember, you're throwing a refrigerator at the US Bank Stadium, and it's just not going to make any difference, right? Also, aluminum, I don't know if anybody saw it spectroscopically because it would get vaporized in the process or not, but it would not contribute to the polarization signature, right? That's an interesting question. What happened to the aluminum? Yeah. Okay, so these days, the kind of equipment you amateur astronomers can get your hands on is astonishing compared to when I started graduate school, right? You have stuff that I would have dreamed of having back then. But there's one way to look at objects in the sky that maybe you haven't looked into much, and that's to look at the polarization. Now, it is plausible that you could, given that most of you have imagers, or there's some at your observatory that you have. I'm pretty sure you have some CMOS and CCD imaging capabilities and whatnot. It's not super cheap to do polarimetry, but it is plausible, and it is something that you could do in the context of amateur astronomy. And it might be kind of intriguing and interesting to do that. So what I'm showing you here is a Wollaston prism. If you can find a Wollaston prism, go down the street, some guy with their jacket, like this. That will split the light into two perpendicular polarizations and send them out at two angles. And you can put one half on one side of your CMOS detector and one half on the other side of your CMOS detector. And now you've got this. Then you can use a half wave plate in front to rotate that to 4 total positions, and that'll give you all you need to know to get the fractional polarization and position angle of something, right? This is a little add-on to our 60-inch that we have down at Mount Lemmon. 60-inch today in mainstream astronomy doesn't sound like much, and it isn't, although it's been converted into a completely robotic telescope that is looking for things that go bump in the night. Basically, that's all it's doing. But we have an imaging polarimeter on it that we used a bit, and then when we stopped using it, we gave it to the University of Wyoming, and they put it on their 90-inch. And I just show this just to show you that it's not a big, messy, complicated thing. One point right here is a focal plane aperture. So what you're doing is you're putting in a rectangle that blocks off half of your CMOS detector. It just sits right in the center. And then when you're going to take that and split it into two and fit them next to one another. And I'll show you a picture of that in a moment. Then there's just a collimator, a Wollaston prism, and a half-wave plate in front, and the half-wave plate's run by a stepper motor with, you could, 3D print your gears, get a little stepper motor, which are easy to find. And the amount of things that you can do as a robotics type today is just absolutely amazing to me when everything costs a fortune. Then a camera lens, and then there's just a plain old cooled camera at the back. So here's an example of one of these images. On the left and the right, those are this object, which just happens to be a star, so it's not very exciting, in two mutual polarizations. And I can then rotate that on the sky by turning my half wave plate that's in front of the Wollaston and take another image then take another image, and then take another image, and those 4 images with each side will tell me all I need to know about the linear polarization of this object. This is the CAD drawing of that thing. It was that the filter wheel is one that you can find in the back of Sky and Telescope magazine and things like this, or very similar ones. It's just a wheel that you can buy with a stepper motor, and it's all machined for you, and you slap it in there, and you've got a filter in front. And right behind it, you can see the gear driving the half-wave plate and a little stepper motor in a square box. And then there's a wall sit in there, and then there's the camera on the back. All right. And then this is, over 10 years old. So by today's standards, this is primitive detector technology. This is the one that we built that goes on the MMT. That's the 6 meter. So that's a big telescope. That's down in Arizona. And University of Minnesota has time on the MMT, and we use it because it has an adaptive optics secondary. So the secondary mirror on that telescope can change its shape and tighten up and give you very, very sharp images that you wouldn't be able to get at otherwise. Now, why is that special on the MMT? Because it's at the secondary, so there's no off-axis reflections. Remember what happens when the light comes off the floor? It gets polarized. Well, when light bounces off of mirrors at angles, it gets polarized, and that's bad. You want to look at the real thing from the star in the sky. So the MMT, the light comes down to the primary, goes up to the secondary, goes down into my instrument, straight on through with no off-axis reflection, so we have no instrumental effects, right? So collimator, half-wave plate, Wollaston, camera, and focal plane. That's all there is to it. Now, some of you have seen pictures of 1987A. This was the supernova that blew up in the Magellanic Clouds back in the early 90s. And the HST's been taking pictures of it ever since. And you can now see that where the star was that blew up, there's a ring, and then there's these 2 rings out to the outside. And you constantly hear people telling you this was all because of mass loss during the red supergiant phase, before this star became a blue supergiant and blew up as a supernova. But there's a phase in between red supergiant and blue supergiant that they have to go through, and it's called a yellow hypergiant phase, of course, right? Blue, yellow, and red. And that only lasts a couple of thousand years. In other words, humans have been writing longer than these stars live between being a red supergiant and a blue supergiant, which then eventually blows up in a supernova. Well, can I give you an example of one of those? And the answer is yes. And this comes from that instrument I just talked about. This is a star called IRC 10216. Don't you love astronomy names for things, right? That was the infrared catalog, 2 degrees, 1016 right ascension and things like that. It also has a variable star name now, right? And the reason it's famous is because it was hugely bright in the infrared and hardly there at all in the visible. And that's because it's shrouded in dust. Now, if you then this is the HST image over here. We took that with the HST. And then the one on the right is from the polarimeter on the MMT. That's from MMT pol. And that's in what we call polarized intensity. In other words, it's only the polarization. None of the other light is in that picture. And what do you see? You see a donut. Okay. This star, as a red supergiant, probably had a spherical wind. But as a yellow hypergiant, it made a disk. And you're looking in that disk pole on. You would never know it's there if you didn't see it in polarized light. But you're looking like at a plate, pole on, and the star is spinning like so, and its North Pole axis is pointed right at you. And how do we know that? Because we could take a picture in polarized light. Now, you're not going to be able to do this with kind of sub-arc second resolution or anything like that, but there's a lot of things out there that are kind of interesting that you ought to think about. just want to put a little, the last time I was here and talked to you folks, I did the same thing. I pushed polarimetry and everybody goes, oh yeah, sure, right. But just thought I'd bring it up again, see how it goes. Okay, that's it. That's all I have.
What?
No, it is.
What about now? Oh, there we go. All right. Anybody have any questions? Hold on.
What?
The scale on the photo before.
This is 1 arc second.
Oh, you want to go one bar back? Which one?
Oh yeah, that's a good question. I'm not sure I know that, but it's like 10 arc seconds or something or so. You needed the Hubble to image it, but it wasn't hard for the Hubble to image. MMT pole has the same spatial resolution as the Hubble, right? So this thing down in here is the remnant of that disk that was around that star. And this is the bipolar outflow. Imagine 2 cones coming out. And one cone is here and one cone is here and the disk is here. And then the star became a blue supergiant as this stuff expanded and then blew up as a supernova, lighting up the ring and lighting up the edges of the cone. Maybe. Yeah.
All right, so do you have any information on the follow-up to DART, the Hera mission? Supposed to be launched?
No, I don't. I didn't.
Okay.
Right. They didn't do any polarimetry.
Hold on, Dean. One more second.
Thanks. So on the next slide, what's the color scale on the image on the right? Is
The previous slide?
or the next? Yeah, the
Yeah, that's just
is
my
the-
graduate student's idea of how to make the picture look nice.
is the green negative or is
No,
it-
green is
very low?
brighter than yellow, which is brighter than red.
Oh, okay.
And
gotcha.
what you're supposed to notice is that the green is smooth. It's not going like this in brightness. It's coming up and then flat. So it's a flat disk that you're looking at there.
Gotcha.
And the reason polarized intensity picks that out is because you're only looking at scattered light. You're not looking at the star. The star itself is so freaking bright that we had to block it anyway, but there's no stellar light in that image because you've taken it all away. You're only looking at the scattered light.
Yeah, a question about the previous image again, the SN 1987A with the 2 cones. What's lighting up the cones, is that direct emission or is that a light echo from the supernova?
It's partly, it's mostly when the blast wave hit it, is my understanding. Right. It's been, I don't know, 20 years now, or 30 years since the dang thing went off. And that's 30 light years is huge on this scale, right? So it's the blast wave.
It's 1987A, right?
Yeah.
Yeah, so going on 40 years ago.
Yeah, it's going on 40 years. Oh my God.
Time does fly.
Yeah. Although this isn't yesterday's image, this is from some years back, but
And isn't there some saying about that the blast off from the DART mission is giving us a meteor shower that's now man-made?
that I don't know. Good question. Do you folks know? Is there stuff coming at us from?
What? No? No? Okay. All right.
I don't
Fine.
know if the Didymos is on an orbit that's conducive to that.
Okay.
Certainly, it's
It would
not
be
going to make
cool.
it to us just because it got blown off,
Right.
because the solar system's one big place.
Very true. Very true. Are there any online? No? All right. Okay, well, I thank you very much, and Professor Jones.
Thank you.
All right, I'm going to stop sharing here because that's pretty much all we have tonight. Just remember, yes.
Since Larry retired, he's gotten a lot more work done. How about you? I retired in 2018, a little before Larry. And it was the best thing I ever did.
Oh, you
Right.
need the microphone to answer him.
But it was the best thing I ever did, in the sense that I could just do what I wanted to do now. That was great fun. But one of the reasons I retired was to get out of the cycle of having to spend hours and hours and days and days and days writing proposals to get money. So I don't have the money to do things that I used to be able to do, and that's the price you pay for that, right? But hey, that's okay.
All right, wonderful. Thank you. You got a question?
Yeah, have you thought about doing astronomy as a hobby now? I've heard of a club in town, they say it's great.
That's a good That's a good question. I have to think about that one, right? If anybody wants to do polarimetry with their telescope, let me know, right?
I'm sure that there are some people here. I know we have plenty of people that do regular
Well,
imagery.
is anybody here in the AAVSO?
I know a couple people are, but I don't think they're here tonight.
Okay, because that's just plain old boring photometry. You could be doing monitoring the polarization.
I'll put you in touch with Anton. I think
Right.
he's doing some of that.
If you can get photometric accuracy of a few percent in a few minutes, you can do polarimetry. Well, yeah, it depends on how bright the object is, right?
Object brightness over size.
Yeah.
All right, hold on. $500
Okay, yeah,
for the
that's
prisms.
kind of the problem with them is they're not cheap. Right.
Oh, see, I thought that was cheap compared to some of our telescopes we bought.
Really? Yeah.
Yeah.
And the halfway plate's hardly anything at all. And you can get the lenses from Edmunds, they're cheap. And just get your 3D printer and some guy in the aluminum shop and bingo. Yeah.
Mhm. Yeah, Chris will do it. Why is the prism so expensive? I don't know. Glass. Mhm. All right, thank you. All right, before we leave tonight, as a reminder that nominations are from here on out to November 6th by 9 p.m. Email it to boardmember2@mnastro.org, and it has to be in writing. And then we'll have, online for November 7th. Unless something changes, we'll let you know. Otherwise, online. And then December 5th is our meeting where we will actually need our quorum. So please tell people to be online, come in person, so we can meet that quorum and elect our new officers. Thank you and have a good night.